You're just not
when the D3 just stops so that the jQuery comes out. Yeah, I use the element kit.
Yeah, no, I use that for a lot of things, and then like other things you can do. Like before, that was
This whole thing has just been absolute scrumptious.
I guess
Ever since I started, everything I write is stuff that's
every assignment. Maybe I should drop out of software.
I remember basically I love this class because it's forcing me to get outside my comfort zone, learn new languages. I hate this class because every time I have to do something like a 12-hour endeavor, it's a garbage in JavaScript.
The issue with using JavaScript is that you're using JavaScript.
Numberify. This. Oh, you like my SVG? I couldn't quite get it to do the G.G.
My SVG this project, I didn't have to hear it, so I like if the SVG had an interpreter that would make a new SVG with an ID that was like one higher than the previous, so I could hide that.
It's so
It's literally hiding that every time. I
accidentally circled the secret stuff.
Actually, no, yeah, that's not true.
Please read.
I accept it.
Now
I try to machine.
This is like a quintessential GitHub letter where I can pull up someone's code and it's like, oh yeah, this tool totally works, except for this one use case, in which case it blows up. I haven't fixed it.
So this is your capstone project?
No, my capstone project has no code on it. I have a meeting. I finally have a meeting with my sponsor right now. So I can finally give them the game designs that we had, so I can finally start programming. It's for my capstone. I don't have a non-disclosure, so I can talk about it.
When you say capstone,
Yeah, so I have a bunch of sketches. This is what we did. Yeah, like my all work totally. So basically, this is our idea of making a game. And what we do is we do some calculations. You select the best set tiles. Also, so is it straight down like this? So tired. Yeah. We're supposed to be kind of chill. This is the least credits I've ever had. It's not taking 12. Oh, okay. Yeah, I'm only taking 12, but I'm working like 18 hours a day. It's just a room plus I don't want homework. Plus a part-time job. And I guess, I do handle like all this like in your house. Yeah, right now I'm trying to finish up my stuff from my grad study packet so I can get that out to my professor who said she'd write me a letter of recommendation. So I can actually start working on my actual grad study. Oh God! This class has been great though. I've been really enjoying this. This is like this class is the reason I wake up on Tuesdays and Thursdays. I sleep straight through it. find that it has some practical application.
Great, good luck.
Because a lot of people don't poke and home when they're. And, It worked out like last year.
Yeah.
This is my. I did all this last night.
Okay, that is cool.
Like my class.
I don't know the
Have you started?
or data. Usually.
So this is class function, basically the mountain of iron. Like I started this one, that's wrong. You can like, it's like wrong, it's like 45 inches of steel.
That's the scary project.
So you run around with two shields. You got the shield on there.
Scary just because I don't play we.
Projects, yeah. Basically, a whole man.
Yeah, me close there.
Big man. People demand so.
I can see this. Yes. Okay, never mind. I completely get it.
Well, yeah, see, a big old, that's actually a door, but. So basically, it jumps around. This actually immovable walls, it's just your portable bunker. It's by the end of it, you're like walking these ragged threads, providing allies. That thing.
Okay, so
Sure, you'll tell us.
today I am going to basically quickly review the planning lectures that I asked you to watch over the weekend. So I'll go over your questions as well as anything else that you might want me to talk about. Okay, somebody might be waiting. Okay, and then we'll talk a little about predicate logic.
Recording in progress.
Hello? Okay, good. Okay. So we'll talk about predicate logic. You kind of use predicate logic in looking at the planning descriptions because they use things like on A, B, stack A, B, etc. So, predicate of objects. It turns out that in the context of planning, it wasn't that basically. It is useful to think of them as predicates over objects, but one of the things we'll point out today is that essentially predicate logic can be compiled down into propositional logic. You see what I'm saying? So predicate logic can be compiled down into propositional logic. So that's why it was okay to act as if something like on A, B, which you saw in that planning lecture, can be thought of as on A, B, the fact. It's a proposition. You see what I'm saying? And then in general, then what that means, we'll talk about in a minute, is that if you have, let's say, 10 objects, you have 10 objects, and you have basically, you can, this on XY facts, there will be 100 of them, right? Because you could put any of the 10 objects here, any of the 10 objects here. So on AA, on AB, on AC, blah, blah, blah. Okay. So if you do that, in essence, you expanded the number of, a compact representation of predicates over objects into a larger representation of propositions, but it is still finite. So we didn't have to worry about it. When we go to first order logic, which actually, unfortunately, I won't have time to go into, but I will make available a self-contained lecture on first order logic that is optional. So you would not be asked questions on that, but you're so close to getting it that if you find time, you can watch that lecture, and you will get basically my version of how those logics connect, first order logic and proposition. But I will mention the predicate logic a little bit more today, and then we will go back to what we were discussing at the end of last class, which is satisfiability and CSP search, which I could have restarted from there, but since you in the middle actually saw the planning stuff, I want to discuss that first, and then we'll get to that. Okay, that's what my agenda is. There are 8 more classes, and basically, if everything goes according to my plan, which apparently it never does, next class onwards, we will be starting probabilistic logic, elementary probabilistic probability theory, going from there to Bayes networks and statistical learning. And since we have 8 classes, I might throw in causality and causal reasoning as against correlational reasoning, which is probabilistic reasoning. Okay, so that's basically what we have coming up. Okay, and of course the statistical learning part is learning part, except with the probabilistic statistical foundations. So we'll talk about how we can learn Bayes network structures and so on. So that's basically what is coming up. And then as far as the rest of the semester, current semester is going, the midterm grades have been posted. And I also sent, I think most of you know this, I also sent the current cumulatives as to where you are approximately. Like I said, I basically used some approximate weightings, which are consistent with what we did in the past. For example, I think the project 1, part 1 and part 2 were 5 points each in the final points each, and project 2 was given 7 points. Project 2 was given 7 points. Project 3 was given 10 points, and so on and so forth. I explained all this stuff to you, and I put currently the midterm thing at 15 points, and that's how I got for 57 points. What your current things look like. Okay, there's a bunch still coming up. You already have the neural networks homework and the neural networks project that you're working on. And basically those will be there, and then we will have homework also on logic and planning stuff that we have. Depending on the timing, it might have other topics involved in that. And then there will also be likely Bayes network project, but it'll probably be small. Okay, and then the neural network project, depending on the way that the difficulties you might have, etc., you should keep the TAs in the loop about if you're falling behind in terms of getting the project completed. So if the entire class is behind, then we'll need to think about extending the deadline and so on. But this is not a kind of a plea for you to all collude together and say, no, yeah, we are not at all getting done, in which case, it doesn't work. But anyway, so that's basically what I want to say. That's basically it. Okay. So one other point is that so I can have, we have enough time that I can have another take-home midterm. Okay, that would sort of have pieces of things that have been covered in the first midterm, as well as things that got done up until that point. That will be in about 2 weeks time. I will have a poll on this. Look out for this. I know normally polls are basically only the losers seem to be doing the polls. That's why I stopped. I mean, I don't know who the losers are because I actually don't know the names, but I mean, only about half of the people seem to care about actually giving the feedback. But this, since your life depends on it, if the poll comes, you might want to vote. Okay, whether you want to have a second midterm. Okay, that's basically where we are. Any questions from you guys? Okay. So, so let's first start with this for the planning thing. I mean, I'm assuming, again, I don't know whether to ask you to raise your hands, etc. But I'm assuming by now, most of you know that if I ask you to see something, if you don't do that, then you will be behind. So I'm assuming all of you looked at those 3 or 4 pieces of videos altogether about an hour or something. So these were in the textbook. I believe this example is there, so I can try to do this here because I didn't do it in that class, in that talk, in that lecture. So this is a very, very, very small cake making example where essentially we are saying you want to have the cake and eat it too, have eaten it too. Okay, so that's the idea. So initial state says have cake, and goal state says have cake as well as eaten cake. Okay, that means you've already eaten a cake. And then the actions here are action eat cake requires that there be a cake, otherwise you can't eat it. Okay, and the effect is that after you eat the cake, you no longer have the cake, and the cake has been eaten. Okay, and then the action bake cake has the precondition not have cake and effect have cake. So bake cake constructs cakes, except this is some sort of a very strange baking where if there is a cake, it would not work. If there's a cake in the premises, I mean, it's some sort of a American Heart Association kind of a baking. So if there's already a cake on the premises, it won't let you make another cake. Okay. So that's basically the way the actions are. Please understand, but you should be able to read that. So the fact that there is a not have cake as a precondition, which is kind of unnatural by your normal way of cake making, because you can make cakes more and more. Cake makers keep on making cakes. Okay, this particular action is saying you can only make cake if you don't have the cake. And given this, again, obviously that the goal is to have cake and have eaten the cake. And clearly you all know what the actions are, I'm assuming, right? I mean, to be able to solve this problem, now that I explained to you in English, what do you do? What are the 2 actions that you have to do? What? Eat cake and bake the cake. Can you bake the cake and then eat the cake? No, because if you bake the cake in the beginning, it won't work. Because there is already a cake, the baked cake would not be applicable. I mean, you have to think like the machine, because this is what you're given. Here are a couple of things to point out. One is that writing this is somewhat more natural. Because you tend to think, in fact, this whole view of precondition effect models basically are kind of folk psychology says that people tend to think of to do an action, what must be true before and what will happen after the action is done. Notice that before this, we looked at actions. And when did we look at actions before this? When did we look at actions at all before this? MDPs, reinforcement learning, MDPs, they all had actions. Right? Did they have preconditions and effects? No, because they were written, first of all, in the atomic level. They were written in terms of if currently you are in this state and you do this action, you will be in these other states. You remember that, right? Previously, we used to think of actions were in RL, in atomic models. Actions are basically transfer functions. transition, I'm sorry, not transfer, transition probability. Transition functions, transition tables, right? So basically, an action would be defined in terms of if you have S1 to Sn and S1 to Sn, and if you do this action in S1, what are all the states you can get to? If it is deterministic, it will basically have 1 in one of the columns and zeros in all other columns. If it's probabilistic, it will have numbers between 0 and 1, positive numbers between 0 and 1 in all the columns such that they add up to 1. That's the distribution. My question is, when I'm thinking of actions this way, are they still writable as transition functions? Are they still writable as transition functions? In particular, think of this world. In this world, essentially, what are states in this world? What are the states in this world?
Have cake, don't have.
Having cake are, so basically there are propositions. Have cake is a proposition, eaten cake is a proposition. 2 Boolean propositions. How many states are there? 4. If you were to write this action in terms of those states, if you act as if have cake and eaten cake is S0, and have cake, not eaten cake is S1, not have cake, not eaten cake is S2, etc. So basically 4 actions, 4 states. And if you think in terms of doing this action, each of these actions in each of these states, and seeing where they take you, that's the transition table. Do you understand what I'm saying? This is the point that you really want to understand, that in coming to planning here, you are essentially having a compact representation of the transition, because the transition now is being thought of in terms of which state variables will be tweaked. Instead of saying, if I transition from this state, I'll go to state number 75. I will say, if this action is done, it takes this state variable and makes it false, or it takes this state variable and makes it true. So the actions are essentially state variable surgeons. They're basically surgically altering the state variable values and thereby constructing the new state. But underneath it all, you can still think of it as transition functions if you want to. There's nothing wrong with that model. That's basically the transition function model is again as fx plus h minus fx, h tends to 0. That's like the first principles idea. But at the atomic level, now we are looking at an abstracted level. We are looking in terms of states made up of state variables. Now you actually can think of this in terms of these facts themselves, such as have dash cake, not have dash cake, etc. They are propositions. Maybe you really should be thinking in terms of predicates with objects, in which case you know that the representation would be even more compact. And when you convert into the Boolean state variables, it blows up a bit more. It blows up exponentially. And when you convert Boolean state variables to states, it again blows up exponentially. So much of what we are doing is going up this hierarchy of abstractions, being able to do things at a fairly high level of abstraction so that you don't have to think of states as black boxes. As I mentioned, the last time you thought about it was when you thought of states in RL being made up of features. They may be real valued features, but they're made up of features. But the funny thing is that the actions themselves in those worlds, those actions didn't have any representation. They were basically, those actions are still sort of in the transition matrix kind of a representation. And you did not really reason with the feature-based representation of the states. You just use the features to represent the value function more compactly. Here we are going to just use the feature-based representation directly. That's what we're doing. Okay, I said that all, I'm just saying it again, just so that you see that they're all connected essentially. Okay, so the other thing I have is, so if I'm doing progression, what do? I basically start with have cake in the initial state. So have cake in the initial state means, what about the value of eaten cake in the initial state? You guys agreed, right? I mean, I basically, they just showed initial state have cake, and yeah, it looks like have cake. But what about that other value? What? So basically, that's where we said, again, there's a whole discussion there in the lecture that you saw, that initial states are assumed to be complete. If they're assumed to be complete, then if you just say what is positive, then the rest are negative. Remember, for those of you who heard this, and I just heard it again, if I said, who are all the people in the class right now, and I'm seeing the entire class, then the rest of the people are not in the class. If I can completely see who is in the class, then everybody else is not in the class. Whereas if I only have partial observability of the class, then I know who are definitely in the class, but there may be other people under the tables, under the chairs, behind the chairs. I didn't see them. At that point, I can't assume that just because I know you are there, I mean, I cannot assume that because I didn't say you are there, you're definitely not there. You may well be there behind. You see what I'm saying? So initial states are assumed to be complete. On the other hand, goal states are assumed to be incomplete. This is how life works. At any given point of time, you approximately know what state you are in, and you have certain goals that you want to achieve. Like you probably know what your state is right now, and you have the goal of getting bachelor's degree. What shirt will you be wearing on the day you got the bachelor's degree? What about your pants? What shoes? How big, how long will your hair be? Do you know the answers to all of them right now? Look at your shirt. Look at your hair. You know all the answers. Currently, unless you can't, you're colorblind and you can't tell your color of your shirt or something, you know your current state. And you have a goal of achieving, which is basically, I want to get my degree. Okay, is somebody trying to know that? Yeah. You want to get your degree. What is interesting about goals is any state where that goal is satisfied is a goal state. This is kind of going back to A-star search, where goal test function might say, yes, you are a goal to more than one state. It doesn't have to be just one state. And it's nice to have goal state be partial, because that way you basically know what it is that you want to achieve without having to tell all these unnecessary details, such as what clothes will I be wearing on the day I would have passed the exam or I would have gotten my degree. And it's similarly in the initial state, it's nice that it's complete, because because it's complete, you know, you can just tell what things are true and everything else will be false. By the way, this is connected to one of the midterm questions. If the state is complete originally, then if you're doing deterministic actions, then you never have to check the state anymore. That means for your initial state, you know for sure what it is, and you're doing deterministic actions, you don't need eyes. Because I've done this action, so I will be in this state, then I do this action, then I will be in that state, and blah, blah, blah. In a simple scenario where you are the only agent, there's no pesky kids, there are no trucks, nothing, and actions are deterministic. Really, there is no difference between seeing the state or not seeing the state, as long as the initial state is complete. You guys get this? Okay. Fine. So have cake really means have cake and not eaten cake. Because the things that are positive are told, others are negative. In the initial state. In the goal state, that's not at all true. In the goal state, I tell you what I want. The rest of the state variable values, I don't care what their values are. It's not that because I didn't say anything about your shirt, you're not supposed to wear a shirt, or God forbid, you're not supposed to wear pants. That's not what I meant. I just said, I don't care what sort of shirt, if any, you wear. I don't care what sort of pants, if any, you wear. I don't care how long your hair, if any, you have by the time you graduate. Some of you will be bald. Okay? All I care is you graduate and you make a plan to graduate. You get that point? So it's a minor distinction, but it's actually a huge flexibility. It's this flexibility that comes and bites you when you try to do search in the backward direction. You guys see that? Remember, the progression was easy. Progression was almost, I know the complete state, I know the action, I know the next state, I know the complete state, I know the action, I know the next state. Regression really is set of complete states. Because if I give you a partial state, that means any state that is consistent with that partial state is a state. Right? And that's why it becomes hard to get the regression right. And in fact, it's not even obvious in an atomic sense. What does it mean to do search from multiple goal states parallelly to see which of them reaches the initial state? If you think about what happens in the regression, that is what is happening. I'm basically, so really, you want to graduate. So you start doing backward reasoning from, I want to graduate. So you're going to be, there are many states where you are graduating, depending on the expressiveness of the world you have. You can have, you're graduating with a green shirt, graduating with a red shirt, graduating with yellow pants, graduating with long hair, all this stuff. When I regress, in essence, I'm regressing over, basically I'm searching over all these complete goal states to see which of them will reach the initial state. Some of you probably will be broke by the time you graduate, so you may not have money to buy pants and shirt. You understand what I'm saying? Maybe none of you, but some people might not be able to achieve some other goals. So if graduation is the only thing that is important, then you basically see if any state in which you have graduated, can that be taken back to the initial state? Then you have a plan. Because you're doing this, that's why regression becomes hard. You guys get this now? It's actually a pretty smart idea. And there is no equivalent for it in the atomic representations. Seriously. Okay. There was a raised hand somewhere. Okay. So then I have cake, not eat cake. So then if I were to, can I do action bake cake here? Can I do action bake cake here? No. Because bake cake requires the precondition not have cake. And that's not true. So bake cake cannot be done. And similarly, can I do the action eat cake? Yes, because eat cake requires that have cake is true, and that is true, at which point eat cake gives a new state where it says, by the way, even though this is an extremely simple word where the effect winds up telling you what happens to both of the variables that you have, you know from the blocks world example, that actions only tell you which variables they change. And the rest of the variables just carry their value from the previous state. Yeah.
Why do we not use bake cake as one of the other state variables in this?
No, you could. That's your model. Right now, you use this as the representation model. First of all, by the way, bake and there is a semantic difference between, there's an eat and bake are action names. They are not state variable names. There's a difference between actions and states. Before itself, you knew that there was a difference between action and states. Now you are saying there's a difference between actions and state variables, and states are made up of state variables. You used to call them features in reinforcement learning. Control theory people and planning people, they all call them state variables. Yeah.
Okay, so if I'm understanding this right, this is almost like a state machine that you're trying to draw. Like each state is determined by a certain collection of variables. In this case, whether or not a cake is had. And the only way that you transition is by doing an action.
Yes, you are defining an implicit state machine,
Yeah.
where in fact the finite state machines, etc., still look in terms of black box states. They go from S1 to S2, S1 to S3, etc. Here, the states are made up of state variables. So if I basically tell you my representation has 10 Boolean state variables, that means I have 1024 states. And actions take me from one of those states to another of those states. If they are deterministic actions, which is what we are looking at, an action will take you from one state to another one other specific state, if it can be done at all. Okay, that's basically what you're doing. And you're representing this again, just like a star search. Remember, we made this whole point about a star search versus graph search in data structures. The difference is in graph search and data structures, you provided the graph extensionally. That means the entire graph is in front of you, you see it. In a star search, the graph is implicitly defined. It is defined in terms of the state and the child generator function. So you never really have to look at the entire graph. You are basically expanding just the right parts of the graph to get to the goal. That's what A star search was doing. That's what all searches were doing. That's a big difference between 310 graph search and A star search. Implicit versus explicit representations. And this is even more implicit because you are representing stuff at the propositional level, which will then correspond to a state level graph, on which you are searching. Okay. In fact, all of these are called lifted search. Instead of, basically, especially for regression, you already realized that a regression, a partial state is really a set of complete states. And when you're regressing over a partial state, you get a partial state, that's another set of complete states. And I made a huge deal in explaining the regression that the problem is what looks like flexibility can also be a bad thing. You might think that you have a set of states and the set happens to be empty. Remember, there was this nice example where I'll show, remember the example in the regression. Yeah, this one, right? Remember, one of these things cannot be done. Holding A, so not clear B and holding A. Yeah, this one. This looks like a state, not clear B and holding A. And we kind of realized that it's not physically possible in a two-block scenario to be holding A, in which case the hand is holding A, which means B is on the table, which means B is clear. That's not possible. You remember that whole discussion we had in that thing, right? And if you don't realize this, you will expand this further. And remember what I just said last time. Expanding dead nodes is a dumb idea because dead nodes will give you more dead nodes. which will give you even more dead nodes. That last time we talked about in the context of partial assignments for a set of Boolean SAT variables. Here you're talking about it in terms of states for planning. You see what I'm saying? Again, the same idea. If you can tell something is dead, killing it and removing it from the open list is the best thing to do. But telling that something is dead is not as easy. In fact, that was a big argument I made. To realize that this cannot actually be reached from the initial state, you should try to actually solve that problem and see you fail. That's extremely costly. You guys see what I'm saying? Okay. Anyway, so that was the point of, I think there's something there. Back. Yeah. Yeah. So eat cake will give me what state? So it will have not have cake and eaten cake. And the difference is here, as I said, the action gave the values for both the variables. But in the blocks world, if you remember again going back there, in the blocks world scenario, you had more variables. And when you did pick up A, it told you pick up A will tell you holding A, not clear A, not on table A, not hand empty. Those are the things pick up A will tell you. The rest of it, the rest of the world, the objects and their placements just carry over from the previous because I didn't touch them. And in fact, this is a huge advantage to think of actions in this local change way. Most actions, if we are actually alive on this planet, it's because we found that things we do tend to have local consequences. How many of you heard of the butterfly effect? If butterfly effect was all over the place, we'll all be dead. We won't be talking about butterfly effect. You guys realize that? There is a name called butterfly effect because most of the actions don't have huge consequences that are non-local. That's how we live. And that's what these kinds of representations, action representations, try to capture. There is no distinction between having local versus non-local consequences if you wrote the action as a big transition table. State 1 to state million this side, state 1 to state million this side, and writing probabilities everywhere. Are the zeros and ones everywhere. At that level, pretty much, whether there is an action with local or without local effects, they all look the same. They all look like essentially transition matrices. It's the same thing whether you do object-oriented programs or Fortran programs. The Intel processor gets Intel assembly code. Doesn't say, oh, looks like this is object-oriented program code. No, it's just assembly code. You see what I'm saying? You wrote object-oriented programming because that captures the kind of world about which you're trying to write programs more compactly. Okay. Okay, so that's about that. And then let's go to the other direction too, and then we'll call it a day as far as this is concerned, as long as you don't have any other questions. Okay, so I'm going to start from backward side. So actually from here, if you continued the search, you can expand this state, right? And one way it turns out that in trying to expand this state, the only thing you can really do, the only thing you can really do is to bake cake, because eat cake is no longer applicable in this state. And so you do bake cake and you get a state. that winds up having have cake and eaten cake. Now here is a case where baked cake only tells you have cake. The eaten cake part just came from the previous state because you didn't touch that variable. You get it? Okay. So that's basically the progression side. And in fact, the search here is again, what action to pick and how to expand the tree. And if you're coming in the backward direction, what happens? If you come in the backward direction and your goal is to have cake and eaten cake. So what can be the last actions? Can, for example, eat cake be the last action? Why can't eat cake be the last action?
It takes, it is not have cake.
That's the reason. I hope all of you understand. Don't use your semantics of cake eating, because we already know that your semantics of cake eating is not the ones this domain is using. You won't mind making more cakes when you have eating more cakes. This one requires one cake at a time. The real reason eat cake is not possible is because if eat cake is the last action, then it would ensure that after it, not have cake is basically plugged in. You want to clamp not have cake. But you require have cake in this final state. And if you're the last guy, then that's the end of the plan. You guys notice that? So that's why you can't do eat cake. That's what the regression thing tells you, that you cannot apply the action if there are two reasons. There are two things that we said about applying the action in the regression way. I'm sorry. Yeah, an action can be applied to this is progression. Of course, action can be applied when the preconditions hold, in which case you compute the next state. For the regression, a state S can be regressed over an action A as long as there is no state variable such that the variable is given different values in the state and by the action. If the action says this variable must be true and the goal state says this variable must be false, you can't have that because this is the last action. You see what I'm saying? This only requires, so now this piece basically makes sure that at least nothing is killed from the goal state. Then the other thing is the action useful? Is it doing something useful? For it to do something useful, you might want this second part, which is there at least exists one variable v dash such that v dash is actually given the same value by the effects of the action as well as the state. And that's why I said this part is first do no harm. And this part is, if possible, do something good. Right? The doctors are taught, first do no harm, and if possible, do good. Okay, so regression essentially ensures that the first condition is required. In fact, it turns out that if you have to relax one of these conditions, you can avoid checking this. That will just give you plans that are executable, but longer than are needed. Because if the last action isn't doing anything useful, then the guys before it still have to do everything useful. But if the last action kills the goals, then the guys before can't help. You see what I'm saying? So if you actually relax the second condition, then you can have plans that are non-minimal. That means they will have redundant actions. They're actions which are not doing anything useful for the plan. But it's one thing not doing anything useful for the plan. Remember, I mean, you're part of a team, right? I mean, you guys all have these team projects. We know how the team projects work. Like one person does all the work, the rest of the people come on for the show. In fact, there are, I understand, well-established rules in master's level, for example, that the junior students are supposed to do the work while the senior students apply for their jobs and do interviews. So well-established rules exist. So the senior people are not doing anything, they're just coming on for the ride. It's bad from the grade giving process, but at least they're not killing the project. If on the other hand, the senior people try to kill the project by essentially doing wrong coding or something, that's worse. So first do no harm. If you are a part of a team, first do no harm. And then, if possible, do something useful. Okay. Okay. So in this particular case, eat cake is not possible. I can do bake cake. If I do bake cake, what would my state be? Can I do bake cake?
Yes.
Because bake cake requires effect have cake. So actually, not only is bake cake not saying anything that is inconsistent with what the goal state wants, it is actually saying at least one thing that is consistent with what the goal state wants. Yay, bake state is useful and it's a good doctor. So I can allow bake state to come in. And then what happens? Since have cake is being given by bake cake, I don't need to bring it back here. And the only thing that's not given is eaten cake, so that comes here. You understand what I'm saying? And remember that all these states, these green states, and not this green state, these are all incomplete states. So when I don't write values of some state variables, that means I don't care about their values. It's not that I know them to be true or false. Please understand that distinction. It's a very important distinction. Yes.
Is it possible for a variable to never change its value but still be relatively useful to the scenario?
Yeah, it can be, because actually it's a very good question. Like, for example, being alive. Being alive, that song, right? I hope it doesn't change, right? That's a proposition that you hope doesn't change when you're doing actions. But it's a precondition for doing pretty much everything else. It's a great question. Ask yourself those kinds of questions. So for example, in fact, this requires, so one of the interesting things about thinking about planning this way is that here, wish I just added extra things, that here we're talking about goals of achievement. That means, in essence, you're thinking of reaching a state where certain state variables have the required values. It's like the most normal way we think of achieving things. Right? I mean, you have a goal. I want to pass the course, or I want to get a diploma. And then the other pieces, of course, there are multiple ways of getting diploma, and they might have constraints. For example, you might say, I want to get a diploma without going broke. That's a constraint. We, from the university side, we don't like that constraint at all. We should not care. We don't care if you go broke, because if you start worrying about going broke, etc., who is paying the tuition for us? That's your constraint. And in fact, so we will say, it's okay to go broke for a while and you'll get the diploma. Then you take this bank loan, right? You pay. Now we are in good shape. So you all fall for this, you take big loans. That's a situation where it's a constraint, but then it's not a sharp constraint. So I'm essentially saying, I can go broke as long as I take this loan. But then there may also be conditions. So already the not going broke is a path constraint. It's a path constraint. It's not just about reaching the goal, but if you're going broke in the middle of the first year, and then somehow somebody helped you, the question is that a good path or not? And the most classic path condition is get a diploma and not be dead. Stay alive while you get the diploma. That it's very hard to say, yeah, maybe we'll be dead for the first semester, maybe second semester, but then I will be ready for the diploma. That's not possible because you're dead once, you're dead. You see what I'm saying? So then I have goals of maintenance, not just goals of achievement, but path constraints which are goals of maintenance. Right? Goals of maintenance. Again, this is all language that you understand. Right? I mean, I understand that for some reason the class particularly sleepy today, but this is language you understand. You think in terms of goals, you think in terms of reaching goals while satisfying some constraints. Where are goals in reinforcement learning? What is the atomic description of goals? We have atomic description of states. We have atomic description of actions. What is the atomic description of goals?
Absolute error.
What?
Mean absolute error.
No. Okay, I want to add a new slide. Yeah. So basically I talked about goals of achievement, goals of maintenance. We can also talk about goals of cleanup. Remember in your grade school, they told you, you can play whatever game you want to play, but after you're done, clean the damn place up. That's not part of your goal, really. It's just an auxiliary goal so that other people also can play. Right? So you can have goals of cleanup and all this stuff. My question is, in RL, MDP, atomic representations, we know states, actions. States are black boxes. Actions are transition matrices. My question is, what are goals? Yes, you had a question.
I'll ask it later. It's just
Okay. What are goals? Did RL have goals? Again, this is one thing, whether you like it or not, this is one thing you get from my class. Okay. The world is not made up of unconnected concepts. Everything is connected. And in a course, if I just tell you 8 things with no connection, you should think that you wasted your time. There should have been 8 different courses at the minimum. Yes, go ahead.
Is this like a specific kind of state, like an end state?
No. It's a good question, actually. I mean, it's not. That's not. So how do you tell reinforcement learning agent what it is supposed to achieve? Yeah. What? Say it loud. Reward function. Reward function is the assembly language for goals. Just as the transition matrices are the assembly language for actions, and the black box state numbers are the assembly language for the state representation, reward functions are the assembly language for goals. And then one of the interesting questions would be, how do you compile natural goals into reward functions. This becomes an important issue because to the extent you kind of understood these kinds of goal representations, achieve this, don't kill this while you are achieving this, clean up these other, make sure that these other variables get to this recovery value after you achieve. These are natural ways you think about the world. So if you're telling your robot what to do, you are telling your robot what to do, you're likely to think in these terms. And if that darn thing ultimately converts everything, compiles everything down into a reward function, how do you make sure that your goals and the reward function it's using are the same? In particular, all goals will be partially specified. And in so doing, because you partially specified the goal, the reward function, the machine, if there could be a wrong way to compile the partially specified thing. Like, for example, you say, I want to, if you just said the simple thing, like, I want to get the diploma. What if I compile it into a reward function which involves you getting the diploma, but on the day before or the day after you die? And then I will make a policy that will happen. You see what I'm saying? How many of you heard, either in the course or outside, of Stuart Russell's huge big worry that AI will cook his cat? Stuart Russell, for some reason, extremely worried that the most evil thing AI can do is the robot, I'm feeling hungry, and the robot says, okay, I'll cook the damn cat. How does that, why is that wrong? I mean, I'm a vegetarian. Many of you are not vegetarians. You guys eat all sorts of omnivorous stuff. Why not the cat? Do you see what I'm saying? It's quite reasonable for the poor robot to have converted your goal, which involves, okay, there is available, in my case, okay, Ra wants food, there is an eggplant, we'll cook it. You non-vegetarians want food, there is this cat moving around, I'll cook it. When did you tell your robot cooking cats is not allowed? You understand what I'm saying? All goals are partially specified, and we use common sense to consider the expansions of the goal. Strictly speaking, if you just said get the diploma, then any state where the entire Tempe is in flames and you still got your diploma, that's a great plan. So I gave you a plan where you have your diploma, Tempe is gone, the US is gone, all sorts of things, but you got your diploma. The robot says, I achieved your goal.
Doesn't that fall under the do no harm thing then?
No, that's a very interesting question. The do no harm. By the way, these are very important questions. Okay, I mean, notice that you heard this whole lecture and you're still kind of hearing a different version of it. Okay, that's why I was trying to make you do that. Do no harm thing is with respect to the goal you gave. If the reward function doesn't distinguish between you getting the diploma and Tempe being on fire versus you getting the diploma and Tempe not being on fire, then both are good policies. You understand what I'm saying? So this is where essentially this common sense, is involved. All goals are, I mean, this is also the paperclip. Cat. You guys know the paperclip one? Some of you must have heard of the paperclip one. So you tell the robot that, it would be nice to have some paperclips. Can you start manufacturing paperclips? And then it says, what's my reward? Oh, more paperclips, more reward. Soon enough, everything is a paperclip. All the bicycles, etc., everything has been converted into paperclips. And the robot is looking at you saying, hey, where's my reward? So those are all the extreme cases, essentially, of all goals are partial and we need common sense. We need use common sense to elaborate them. There is an example of saying, I don't have common sense, I'm coming from a different civilization. And it's your problem to tell me what you want and what you don't want. And we depend on common sense. The common part of common sense is that we all have the same common sense. And there's no reason to believe that you have the same common sense as the robots. Now, people tend to think, in fact, this is kind of going in a slight digression, but people tend to think that, oh, well, machines can read up web and they'll get common sense. And I actually just tweeted this morning that what you get from large language models like GPT-3 is some kind of noisy wisdom of crowds or wisdom of noisy crowds. And that will actually be common sense only if people only use web to say true things and nothing else. If you're learning stuff from web, it's as much a common sense that water flows downhill as it is common sense that vaccines have RFID, nano RFID chips that Bill Gates has personally implanted. We know that. Most of us already know this. We've been told by Facebook in a meta way that this is true. Right? So common sense is not, I mean, basically, again, it's not that simple to just get common sense by reading up stuff on the web. Okay. Anyway, so keep that in mind, and keep also in mind the fact that goals are essentially a description of the partial state of affairs you want. And as far as converting them into reward functions, then essentially the machine has to figure out how to convert them assembly language. And in general, it's easier for you typically to give goals of attainment, goals of maintenance, etc., than to write arbitrary reward transition matrices. Those are easier to learn. In general, there is a big distinction that I kind of want you to understand, that what is easy for machine to learn and reason with is not the same as what is easy for you to give and understand. You see what I'm saying? And if you're into this, there's actually a paper that our group has, it's on my webpage, called Symbols as a Lingua Franca. And you can read it up, it's a long thing. But basically, you want AI systems to have some sort of an interface layer because they're in our world. And they should be able to talk to us in the terms we understand and take advice from us in the terms we're able to give. Otherwise, for every robot, you need a robot engineer who then winds up sitting in your home. Either that, or at least you should have cats. Okay. One other interesting thing is somebody actually, I mean, I don't think it was in the lecture you saw, but it turns out that this sort of providing goals and reaching goals, as I said, it's the most natural way you can represent what a robot needs to do. So not surprisingly, several game engines essentially discovered A-star search because of planning. And the stochastic ones obviously have to do MDP, but the deterministic ones can do A-star search, but they will think in terms of these sort of actions and preconditions and effects. So that's one example of a like a planning, this sort of representation in a game engine. If you just try to use RL because that's what everybody does, again, think about the following thing. Saying I can do everything in the atomic level is like saying I can do everything in the assembly language. Yes, but why would you want to do it? If your machine is writing programs, it can write it in assembly language as long as you don't have to read them. But if you're writing programs, you're more likely to write them in a high-level language. And somebody else should take the load of converting that into an assembly language. And who is that somebody else? For you guys, compilers. That's the interface layer between computers and you, the coder. That's the thing that you wind up needing, even when you have robots and humans exchanging reasons for their failure, exchange and taking goal specifications. Okay, all of this stuff was there before. It's just that you didn't quite understand what the heck reward function meant. Just like you don't understand what assembly language code is. I mean, the assembly language code can be doing something or other. That doesn't necessarily mean that you understand, when I say I have a piece of assembly language code, you have no idea what I'm talking about necessarily in terms of what its purpose is. Whereas when I start talking about goals of achievement, goals of maintenance and all this stuff, suddenly that's a lot more natural. That's the way you would have provided. Okay. So the predicate logic, actually what I would do is, I should mention this, that, I think this already said this, that predicate logic is things like what you already see, like have cake or on a B, where predicate logic is the world is made up of objects and relations between them. And objects, so when you say on a B, A is a real world object, B is a real world object, on is a representation of a relation between these objects. This is called a predicate. And the predicate holds between these variables, these objects A and B. Okay, it's a very natural way to think about the world. In fact, if you remember if you remember this picture from originally when we started talking about propositional logic, normal propositional logic makes the assumption that the world is made up of statements that are true or false, nothing else. That's the only ontological commitment it makes. Predicate logic, on the other hand, assumes that the world is made up of objects and relations. That's the predicate logic. And if you just add one more thing, objects, relations plus functions, then it becomes first order logic. The reason is that if I give functions, functions take objects and spew out unnamed new objects. You understand what I'm saying? So imagine I have basically some sort of a genealogy table, and there is a Rao, and there is a Tom, there is a Mary, and there is a parent relation between X and Y, if X is the parent of Y. Okay, then if these are the only three objects, then essentially there will be 9 possible predicate configurations. Parent Rao, parent Rao Tom, parent Rao Mary, parent Tom, blah, blah, blah. So 9. If on the other hand, I just add a little function, father of, which takes an object and gives the father of that object, you're screwed. Right? Because I can say parent, father of Rav, father of one extra Rav, one extra father of and Rav. Right? Because father of Rav is the parent of Rav. And father of Rav is the parent of father of Rav. You see, I can suddenly say infinite number of predicate configurations. And each predicate, each ground predicate configuration will convert to a proposition. That means if you convert into assembly language, it will be an infinitely large assembly language. Man, that's not going to work for us. That's why first order logic is actually more expressive. It's like beautiful to be able to talk about infinite number of things in finite sentences. And we can do that. We can do that because at least we can do first order logic. Okay, but even if you don't go up to, that's why you should actually understand how first order logic works. But even if you don't go up to first order logic, predicate logic captures everything except the functions. It's just the functions which then create new objects that kills everything in terms of compilability. You understand what I'm saying? So normally you can think of higher level languages can be compiled down to lower level languages. Except the analogy breaks down when you say that a higher level language such as logic, first order logic, cannot be compiled into predicate logic because the equivalent program would be infinitely large. Which means, in fact, it's a way more expressive way. The more compact way you can talk about large number of things, the more expressive the language is. Which is why assembly language programs are larger than the high level language programs. Now, the reason I brought you all this kicking and screaming is, so basically you can write predicate logic. You can almost think of, I didn't say that you learned predicate logic, but you learned predicate logic in talking about that. And everything you did in predicate, first order, propositional logic, you can use it directly in predicate logic because you can just assume that the parentheses are syntactic sugar and you can compile it down into propositions. Wherever parentheses, you put a hyphen, it becomes a proposition symbol. Do you see what I'm saying? You could do it that way. Now, however, what is more natural for you? You still want to think in terms of parent and people, loves and people. Loves is a relation between people. So in a way, I would argue that Tom is a node, Mary is a node, there is an edge called loves. If I do that, you know what I'm doing? One of the hot things right now. It's called knowledge graphs. Okay, that's the reason I brought you there. Here is a knowledge graph. How many of you heard of knowledge graphs? How many of you have heard of predicate logic or thought knowledge graphs are nothing but predicate logic? So you got something today, even though you slept for the most of the first part of the class, you still remember this. Then you can still do well in your interview. Because knowledge graphs are nothing but predicate logic. In fact, before that, there was this other thing called semantic web. Something called semantic web. Semantic web tried to give a different sugar coating on logic. They actually tried to provide what is called RDF triples, which are basically object relation object. How many of you heard of these triplets, RDF triplets? Semantic web was like pretty hot just a couple of years back. And the triples are essentially ground predicates. And then they also had this thing called OWL, which was the background logical theory in first order logic. For some reason, people like this syntactic form more for a while. And now people like this knowledge graph syntactic form for a while. Which brings me to this quote that every generation of AI has to reinvent semantic nets, because way before when AI started, people will write things like A, some connection to B, some connection to C, some connection to D, etc. And the question is, what's in the connection? And they used to be called semantic nets. In fact, my advisor, his thesis was on spreading activation in semantic networks. Sounds very neural networky because he was actually doing neural networks and it wasn't going anywhere, so he changed. Okay, but the point is that you invent semantic nets in multiple different syntactic forms. There was a KL1 representation at one time. There is RDF-all representation for a while. Now knowledge graph representation. But the smart people understand it's all just predicate logic. And then bring in all your knowledge about predicate logic and you understand knowledge graphs. Okay, I ran out of time, so we will end here.
I have a meeting at
Yeah.